Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about arithmetic and geometric sequences. We're going to differentiate between the two. We're going to write explicit rules for both arithmetic and geometric sequences. And then we're going to find the nth terms for both arithmetic and geometric sequences. All right, so let's start by having you take a look at this table and see if you can write a rule in the form y is equal to x, something times x plus some constant. So I'm going to give you a moment here to think about that, and then we'll come back. All right, so pretty straightforward. You should see that the formula is y is equal to x plus 1. So for every input, domain output is going to be one value, 1 unit higher or greater than the input. So 1, 2, 3, 4, 5, 6, 7 as the inputs, 2, 3, 4, 5, 6, 7, 8 respectively as the outputs. All right, so let's talk about sequences, and then we'll talk about specifically arithmetic and geometric sequences. All right, so a sequence is a function whose domain is a consecutive set of integers. So that means the input will be this consecutive set, typically starting with 1 and moving up 1 unit or integer value indefinitely or limited to a specific set of inputs. So a domain, for example, would be 1, 2, 3, 4, 5, 6, 7, and so forth. So a consecutive set of integers, that would be the domain or the input, and the outputs are going to be the values in the range. We're going to call those the terms of the sequence. And the range, let's say in this case, would be 2, 4, 6, 8, 10. We can have two different types of sequences. One is infinite, where there is an infinite number of inputs and outputs. And then we can also have a finite sequence in which there is just a finite number of terms or outputs as well as inputs. So sequence is a function. Domain is consecutive set of integers. We're going to assume that that starts with 1, so 1, 2, 3, 4, 5, 6, etc. The terms are the outputs, part of the range. And the range will correspond to the outputs corresponding to the inputs from the domain. You either have an infinite sequence or a finite sequence, depending on how we define that sequence. All right, so an arithmetic sequence, what defines an arithmetic sequence is that there is a common difference which is constant between all of the terms in the sequence. So remember, the terms are the outputs of the sequence. So all you need to do is take a look at the difference between the terms, and if it's constant, it's a constant value, then you know it is arithmetic. So the arithmetic sequence rule is a sub n, which is the term value. Nth term is equal to a sub 1, so the first term plus n minus 1 times d, the common difference. So I'll leave you a moment to jot that down. All right, so we're going to go back and take a look at our initial rule, and we're going to start placing the proper values into the rule. So a sub n is just a sub n. For now, we're not sure what that is. It depends on what n is. A sub 1 we can find is going to be the first term of the sequence, which is 2, plus n minus 1. N again is just n, whatever term corresponds to the nth term, and d is the common difference. So we can see the common difference here between 3 and 2 is positive 1. So now we can rewrite the rule using this formula. So a sub n is equal to a sub 1 plus n minus 1 times d. A sub n is equal to 2, that's the first term, plus n minus 1, excuse me, times the common difference. So I'll have to erase that. So it's plus 1 is the common difference. It's times plus 1, so I'll just take that out so there's no confusion. A sub n is equal to 2 plus n minus 1. And if I simplify, a sub n is equal to 1 plus n, or n plus 1. All right, so in an arithmetic sequence, there is a common difference. All right, so the question is this function or this table, does this table represent a function that is arithmetic? And the answer is yes, there is a common difference, and that common difference is 3. Next question, does this table of values represent a function that's arithmetic? And the answer is Note the common differences range between 4 and 5. The difference is not constant. So this is neither geometric nor arithmetic. All right, so let's talk about geometric sequences in series. In a geometric sequence, the ratio of any term to the previous term is constant. And so that ratio is called R. So remember, it's the ratio of a term to the previous term, not the previous term to the subsequent term, which is defined as R. So please don't get that confused. The constant ratio is called the common ratio and is denoted by the letter R. And the geometric sequence rule is a sub n. So whatever nth term is equal to the first term times the common ratio to the power of n minus 1. So again, a sub n, the last or the nth term in the sequence. A sub 1 is the first term. R is the common ratio. All right, so the question is this function represented by the table of values geometric? And the answer is yes. I have a common ratio of 2. So this is a geometric sequence. Now we're going to write the rule. A sub n is equal to a sub 1 times r to the n minus 1. Let's see if you can figure that out. All right, so a sub n is equal to a sub 1, which is 2 times the ratio 2 to the n minus 1. All right, so now we're going to find the nth term in an arithmetic sequence. I'm changing the letters from a to t here. So t sub 3 is equal to 8. T sub 10 is equal to 43. We want to find t sub 150, so the 150th term. So the first thing we're going to do is we're going to subtract t sub 3 from t sub 10 to find the total difference between the two terms. 43 minus 8 is 35. Then we're going to subtract 3 from 10 to find the number of terms from term 3 to term 10. That's 7. And then we're going to divide 35, the difference, by the count of terms, 7, and we're going to end up with our common difference of 5. All right, so now we have the common difference of 5. We need to find now the first term, and we're going to back that out of the value that we have for the third term, 8. So we're going to solve for t sub 1. We know t sub 3 is equal to 8. 8 is equal to t sub 1 plus 2 times 5. So 3 is n minus 1, 2 times 5. We know there are two different terms between t sub 3 and t sub 1. So we can find out that 8 is equal to t sub 1 plus 10, or t sub 1 is equal to negative 2. Now we have t sub, rule for t sub n. T sub n is equal to negative 2 plus n minus 1 times 5, which you can rewrite as t sub n is equal to negative 7 plus 5n after simplifying. And then we can use that to find t sub 150. T sub 150 is going to be negative 7 plus 5 times 150, or 743. All right, so I'm going to have you complete these two problems on your own. We're going to come back and check our work. All right, so for the first one, I don't provide the solution, but I do go through some of the math in the second one briefly, which I will not do for you right now. But you can get that on your own, or come consult with me independently. The answer to t sub 179 is 538, and the answer to t sub 278 is negative 728. So again, you want to find the common difference between the two by subtracting 25 from 61, and then counting the number of terms between the two. So 61 minus 25 is 36. 36 divided by 12 is going to be 3. And in the second one, I have 15, negative 15, and the difference in terms is 5. So negative 3 is your difference for the second. Okay, so now we're going to move on to a little bit more complicated process in finding the nth term in a geometric sequence. We're going to use a geometric sequence rule to write two equations with the givens. The first is for t sub 2. T sub 2 is equal to t sub 1 times r to the 2 minus 1, because it's the second term. So t sub 2 is equal to 64. 64 is equal to t sub 1 times r to the first power. And for the second, t sub 5, which is going to be equal to negative 8 times r to the 5 minus 1, which is r to the fourth power. So negative 8 is equal to t times t sub 1 times r to the fourth. So now we have two. We can rewrite this for two equations for t sub 1. t sub 1 is equal to 64 over r, and t sub 1 is equal to negative 8 over r to the fourth. And now we know that t sub 1 is equal to t sub 1, so we can equate those two values. 64 over r is equal to negative 8 over r to the fourth. We're going to cross multiply and rewrite the function, and then divide the constants and the variables on one side. And we end up with r cubed is equal to negative 8 over 64. Taking the cubed root of simplifying negative 8 over 64 to negative 1/8. Taking the cubed root of these values leaves us with r is equal to negative 1/2. All right, so now we have our value for r, and we can solve for t sub 1, taking one value for t sub 2, which is 64, is equal to t sub 1 times negative 1/2 to the n minus 1, which is going to be 1. Now we're going to solve for t sub 1. T sub 1 ends up being 64 divided by negative 1/2, or t sub 1 is equal to negative 128. Now we want to find t sub 17. We're going to rewrite our equation with the known values. T sub n is equal to negative 128 times negative 1/2 to the n minus 1. T sub 17 is equal to negative 128 times negative 1/2 to the 16th power, and that equals negative 1 over 512. All right, so I'm going to give you a couple of problems to do. You're going to finish these problems. That will be the end, actually just one problem. Let's see if you can find t sub 10 when t sub 2 is equal to negative 18 and t sub 4 is equal to negative 8. I'm going to pause here while you do those calculations. Okay, so you're going to end up with negative 512 over 729. Again, you're going to go through the process of creating two equations for t sub 2 and also for t sub 4, rewriting those for t sub 1. And then you're going to solve for t sub 1. You'll end up with t sub 1 is negative 27. And then solving for r is equal to 2/3. You're going to use that value to rewrite your equation for t sub 10, and then solving using t sub 1 and r to get an answer of negative 512 over 729. All right, that's it for this edition of Ott in Math. Thanks for joining. Catch us next time when we talk about recursive rules for geometric and arithmetic sequences.